In this chapter, we're going to be learning about enols and enolates, focusing on alpha substitution reactions. In this video in particular, we are going to talk about enols, both enol content and enolization, and a little bit on consequences and applications. As we think about enols and enol content, we need to start with defining these. So a ketone or an aldehyde, this is referred to as the keto form, where we have the C double bond O, and the keto form is in equilibrium with an enol form. So the ene because it's an alkene, ol because it's an alcohol. Notice that the carbonyl carbon was connected to the oxygen. It is still connected to an oxygen, but that's now an alcohol. And then either one of the carbons adjacent to the carbonyl becomes part of a double bond. Notice this is an equilibrium arrow, not a resonance arrow, and so there is an equilibrium between the keto form and the enol form. Both of these compounds exist. Okay, these are isomers, not resonance structures, and both of these compounds exist. But the question is, how much? What is the position of equilibrium? Keep in mind, for any type of equilibrium, the equilibrium constant K is equal to the concentration of the products divided by the concentration of the reactants. So in this case, we are talking about the enol over the keto form. So in the case of a simple aldehyde, this equilibrium constant is 6 times 10 to the negative 9. So this is a very small value, which means we have a very, very small amount of the enol form. Most of this exists as the keto form. This is what we're going to have for all simple aldehydes and for all simple ketones. Lots and lots of keto form, very little enol form. And in general, this is because a carbon-oxygen double bond is stronger than a carbon-carbon double bond. But there are exceptions, of course. If we look at this diketone, we can draw an enol form that looks like this. And the equilibrium constant is 0.2. So this is a much larger number than what we had up here, and therefore, although this is less than 1, it means we still have more keto form than enol form. In this case, we have a lot of enol form existing, and this is because you'll notice that this double bond is conjugated to the carbonyl, so giving us a conjugated system that makes this significantly stable relative to the diketone. For the next ketone, we can draw the enol form that looks like this. This is phenol, and we know that this is an aromatic compound. So in this case, K is huge. So essentially all of the compound exists as the enol form, and there's almost none of the keto form. So for most simple aldehydes and ketones, there's lots and lots of keto form, very little enol. For some stabilized enols, there will be a significantly greater amount of enol form compared to that of regular simple aldehydes and ketones. And for something that gives us an aromatic compound, in this case, the enol form is essentially all that exists. So how does enolization happen? Under neutral conditions, the reaction happens, but it's very, very slow. Under acidic or basic conditions, the reaction happens a lot faster. So we're going to take a look at the mechanism, first of all, under acidic conditions. So the carbonyl oxygen of our ketone can grab off a proton from H3O+, put those electrons back onto the oxygen, giving us a protonated ketone plus some water. Now, water can act as a base, grab off this proton, allowing these electrons to fold in here to form the double bond, pushing these electrons onto the oxygen, giving us the enol form and some H3O+. If we look at enolization under basic conditions, in this case we have hydroxide, which can act as a base, grab off this proton, allowing these electrons to fold in here and form the double bond, pushing these electrons onto the oxygen, giving us this enolate intermediate. And we also made some water. Now the enolate can grab off a proton from water, putting these electrons back here, and we now have our enol. Plus, we made some hydroxide. So in both cases, the reaction is catalyzed by acid or by base. Notice that the same two steps happen, they're just in a different order. Under acidic conditions, the oxygen becomes connected to the hydrogen, and then the double bond forms. Under basic conditions, the double bond forms, and then the oxygen becomes connected to the hydrogen. So analogous steps, but in a different order. Now keep in mind that for simple aldehydes and ketones, the equilibrium lies toward the keto form. But you still have to remember that the reaction happens both ways. And so this will be converted to this, and then some of this will react back, some of this will react forward, some of this will react back again, so that at any one instant, if we could take a snapshot, we would have some of this, and some of this. But based on the equilibrium constant, we know that we're going to have mostly this. Next, let's think about some consequences of enolization. Let's say we have a ketone that has a chirality center adjacent to the carbonyl. Well, if this is exposed to a little bit of acid or a little bit of base, then this can isomerize to form the enol. Now this enol form will equilibrate back to the keto form, but as this reaction happens, it will be equally likely for the hydrogen to become connected to the back of this carbon, which would give the original compound back again, but it's equally likely for the hydrogen to become connected to the front of this carbon, which would give this. So at equilibrium, you would have mostly keto form and a little bit of enol form, but the problem is that your keto form would now be racemized. So you're going to have an equal mixture of this compound, and so you've lost the optical activity of your compound. So that would be a real problem. But enolization can also be favorable. We've talked a little bit about using labeled compounds to be able to investigate a reaction mechanism. Well, here's how we can make a labeled compound. If you have a ketone and you treat it with D2O and base, for example, then you can make a deuterated compound. Let's think about how this works. So we have a couple of hydrogens on the carbon that's adjacent to the carbonyl, and following the enolization mechanism, the base can grab off this proton, putting these electrons here, putting these electrons back up here. When this tautomerizes to the enol form, it is likely that the O- will grab a deuterium, because that's what we have present is D2O. So we're going to get some of this, but more importantly, when this tautomerizes back or isomerizes back to the keto form, if the base grabs off this deuterium, allowing these electrons to fold in here, and these electrons are going to grab off a proton, but it's not going to be a proton, it's going to be a deuterium, putting these electrons here. Now what does that give us? we have our carbonyl back, but over here we have one hydrogen still connected, but the other one is now a deuterium. So because this reaction is at equilibrium, then this can keep happening, going forward and back, until eventually both of these are replaced by deuterium, and both of these hydrogens are also replaced by deuterium. So this compound could now be used in mechanistic studies, including enzyme investigations. One other application of enolization is an alpha halogenation reaction. And it's actually this reaction that provided the evidence for the tautomerization mechanism that we talked about. So if we have a ketone, and this is treated with bromine and water in the presence of acid, then this is the product that can be isolated. All right, so how does this work? Well, this can be tautomerized to give this compound, and now this compound can react with bromine. The oxygen can help out so that these electrons come here, making the alkene more nucleophilic, so that these electrons can be shared here, pushing away the bromine, giving us, this is a double bond here, positive charge. This is connected to the CH2, which is now connected to the bromine, and then some water, the solvent, can grab off this proton, put these electrons back onto the oxygen, giving us this product. Another example would be using chlorine or iodine, and the H+, it could be a little bit of HCl, it could be some acetic acid, for example. And if we start out with this aldehyde, then we can make some of this. If we have a ketone, for example, this reaction can work, but if we have an asymmetric ketone, then we are likely to get some of this and some of this. So there's a limitation. Here we have a symmetric ketone, and so this can undergo alpha halogenation to give some of this. And then this compound can be treated with pyridine, and this will undergo dehydrohalogenation so that the base will grab off this proton, these electrons fold in here, push away the bromine as a leaving group, giving us this compound, which is a conjugated ketone. We've already seen some important reactivity of alpha-beta unsaturated ketones, and we're going to be looking at these further in the next chapter. So this is one very useful application of alpha halogenation, is to prepare an alpha halo ketone, which can then be converted to the alkene. So that takes care of what I wanted to mention regarding enols, and think about the negative consequences as well as the applications of enols.